Okay, let's take a look at vertex form for a quadratic function. That is to say, this form right here on the left, we say that y is equal to a times the quantity x minus h squared plus k, as opposed to our normal standard form for a quadratic function, which is this excuse me, polynomial form where we have it in standard form, ax squared plus bx plus c, and all of our exponents go in decreasing order. The beauty to having something in vertex form is that it simply just tells you where the vertex is, because as we should know from our translations of functions and stretching and shrinking of functions and reflections, our h value here really causes horizontal translation. We can always recognize the horizontal translation because it's the constant that's in here bundled with our x value. And our k value out here, this is going to cause vertical translation. So with respect to vertex form, the reason why we call it vertex form is just because, let's say I have a function in this form, y equals a times x minus h squared plus k. Right now I'm going to say that my a value is just 1. And so this would be the same a value that we put on our parent function y equals x squared, but it would mean that we have the same width as our parent function, and our h and k are both 0 and 0. So if I start tinkering around with our h and our k here, you can see that h is really just shifting our graph left and right, as I've already mentioned, and the k value is shifting it up and down. So much so that if I were to say that, well, normally your parent function y equals x squared, okay, what are its h and k values? And I'm going to go ahead and retype it down here. But specifically write 1 times x minus 0 squared plus 0. So because h and k are 0 on this one right here, then it hasn't shifted left or right at all. Then our vertex is normally at 0, 0. But the moment I start taking h and k and playing around with them, let's say I make h2 and I make k3, what you're going to see is that the vertex of this new parabola is actually at 2, 3. In other words, if it shifted 2 to the right of 0 and 3 above 0, then it would be at the point 2, 3 respectively. Or in general, I suppose we could say that because h and k always tell us respectively horizontal and vertical shifts, well then your vertex is always going to be at whatever the heck h and k are in the first place. So I suppose that some pretty basic knowledge that we want to know about vertex form here is that the vertex is always at h and k, and that h is backwards and that k is honest with us here. Okay. Otherwise, what else would I want to know about our vertex form here? Well, I want to know that the axis of symmetry, which is this imaginary vertical line that runs through our parabola, exists, and I would want to be able to find its equation. So for instance, with this function that I've got right here, I suppose I'm referring to the one where our h value is 2 and our k value is 3 here. We could imagine that a vertical line running through this here would have to pass through the same x value as the x value of our parabola. And so our x equals 2 line gives us the equation of our axis of symmetry. But the thing here that I want to really point out is basically that the axis of symmetry is always x equals whatever the h value of your vertex is, or the x value of your vertex is here. So with respect to vertex form, we would say that the axis of symmetry is always this line x equals, and it's going to be the same x value that we have our vertex in the first place. So essentially, in a nutshell, we would say that every parabola that's in vertex form, its vertex is given by some h and some k, and its axis of symmetry is defined as x equals h here. Okay, so our goal is going to be able to put this in vertex form just so that we can easily find, say, where a vertex lies, and then from there we could use our a value to just graph the rest of our graph. I suppose what I mean by that is, let's say h and k are 1 and 1, I shift right 1 and up 1. Well, if I start messing with my a value, what you're going to see is that we're messing with the vertical stretch of the graph as well as the vertical shrink of the graph. Okay, and so our a value, if our a value is bigger than 1, we're going to get some stretching happening here from our parent function. Let me turn the parent function back on. But if our a value is less than 1 but bigger than 0, we get some shrinking that happens here. And lastly, if our a value is negative, let's make it a negative 1, you can see that this graph here would have the same width as our parent function but open downward. And so with respect to vertex form, this a value is always going to dictate where that 0.11 would have been on our normal function here. Let me get this out of the way. 1, 1 is on this parent function here. Basically, because we are going to stretch or shrink the graph by a factor of a vertically, then that means we're going to take the y value of this 0.11 that's always at 1, 1 on the parent function, and we're going to multiply the y value by whatever the vertical stretch or shrink factor is, which is a. So let's put it this way. If I'm traditionally at 1, 1, in this case, because my a value is negative 1, then instead of going 1 to the right and up 1, I'm going to go 1 to the right and negative 1 times my original height, which is 1. And anytime you multiply by 1 here, which is our original height, you're going to get the same number you started with anyways. So this a value right here is literally dictating that as you go one to the right of your vertex, wherever your vertex may be, that's how far up or down you would go to hit the next point on your graph. So for instance here, I would say that if I had -1, let me type this in here. I'll fill in for my a here. A is -1. We have my h value here is 3, so we're going to have x minus 3 squared. And then in this particular case, I have for my k value, looks like +1. So I will get this graph out of the way. But essentially, you can see that this graph here goes 3 to the right and 1 up. That's our vertex, h and k. And because my a value is -1, okay, as I go to the right 1, that would mean that I'd have to go down 1 before I hit my graph here. So having something in vertex form is a gift because you can clearly see, okay, the h and the k where your vertex lies. You could clearly get your axis of symmetry that runs right through the vertex, and then you could graph it just by using the a value from your vertex to find one more point on your graph here. So just as an example here, let's just go ahead and sketch a few of these. I suppose that in vertex form, if I had something like 2x minus 1 squared plus 3, how would this look? So pretty simply put, we would say that our vertex is at h and k. Our h value is actually a +1. Our k value is a +3. Excuse me, and our axis of symmetry then would have to lie at x equals 1. And so to sketch this, we would just go 1 to the right here, and say here's my axis of symmetry. I would go 1 to the right and 3 up to arrive at my vertex here. And because our a value is positive, I know this is going to open upwards. I'm going to label this kind of underneath it here. We say 1, 3. This a value tells me that as I go 1 to the right of where I shifted to, this is how far up or down I would move. And I would go up 2. So that would put us here at 2, 5, and because of symmetry at 0, 5, this would be on our graph right there. How about instead we would do this? How about negative, and this time I'll do x squared plus 4. Interestingly, this is in vertex form. It's just that we tend not to write things like this if we just don't see an h value, and I clearly don't see an h value. I clearly know this is a k value because if it had been an h value, it would have been bundled with our x here. And so what I can see is that our vertex would lie at 0, 4. That'd be this point right here. Okay. Our axis of symmetry then, AOS, would have to run through x equals 0, the same x value here as we have at our vertex, x equals 0. And because our a value here is -1, a is -1, that means that as I go 1 to the right from this point, I'm going to go down 1, and that point would have to lie on our graph. And because of symmetry, I know that this point would also have to lie on my graph. That's how you can pretty quickly sketch vertex form parabolas just by having this in vertex form.